Okay, so what are the class of functions on which we apply Laplace transform? Because we cannot apply Laplace transform on all the functions. So we call these functions of exponential order. So you can find out the Laplace transform of the functions which are of exponential order. You can see that you never find out the Laplace transform of e raised to t square. It's not possible because it explodes. And you cannot find out the Laplace transform of 10t, but you can find out the Laplace transform of, I think, log t, because you know very well it comes down and it is continuous, it never explodes, but the problem is 0. But 0 is not a big deal, you can deal with that problem. So, and when you evaluate the Laplace transform of log t, there's an integral you will evaluate and you will get the things that what happens. So, a function is said to be of exponential order if there exists some constant Cn to be greater than 0, and let's say some t is greater than 0, then what happens that the absolute value of your function can be estimated by e raised to ct times some fixed m for all t greater than t. When a function satisfies this particular property, we call it the function of exponential order. It means the value of your function is less than some exponential e raised to ct. When the value of your function is less than some exponential, we call your function to be of exponential order. And what should be the coefficient of this t? This t should be linear and the coefficient of t can be anything, 1, 2, 3 or whatever, and this m can be anything. Now you see, exponentials always go like this, exponentials. Then my function is, let's say t, it goes like this. So this t is always smaller than this exponential, we call this t to be of exponential order. And when you take t square, it also goes like this. And it never crosses this because this will go up fast than this one. So this is t square is also less than some e raised to ct, and t is also less than some e raised to ct. Sin t is also less than some e raised to ct because sin t goes like this. You know very well. So these all are functions of exponential order. You can find out the Laplace transform, but this is not okay. Because you will say that, okay, I am taking the value of m to be so much large. But the time will come when this value will cross this value. Because the power here is t square, the power here is t, which is linear. Whatever coefficient you put here, whatever. But this will cross that one eventually. So this is a problem, you cannot find out the Laplace transform of e raised to t square. Because it does not satisfy this property. And this property is what we call the functions of exponential order.
We can say that the growth of exponential function is greater than
yes. Growth of this exponential is greater than a function, then this function is called of exponential order. Or the growth of this function should be less than the exponential. So that's the problem with these.
But t must be linear, the small t.
Small t? Yes. This exponent, the power of exponential should be linear in this case. So
you are writing capital T.
No. This is capital T, the time.
Okay.
It means, let's say, t square will be greater than this value, for example, for some time. Then the time will come. After that time, this t square will always be less than that. Let's say for now it is going to be very small, but after some time, this value will go more fast than this t square. It means we are going to define a situation that this t is that situation. So, is this necessary condition or sufficient? Is this necessary or sufficient, and what do you mean by the sufficient condition?
This is necessary.
This is necessary condition. It means
That surely hold.
it means when this thing holds, then
Then we can say that Laplace transform
Exist. Okay.
exponential functions.
when we find Laplace transform, then this condition will always hold. If this condition holds, then it is not necessary that we can find out the Laplace transform, because there are some functions, you know very well. What is the function? T power minus 1 is always less than this particular function, but we cannot find out Laplace transform. We cannot find out the Laplace transform of this function.
The necessary not sufficient.
This necessary condition not sufficient. Okay, so readily we can define some inverse transforms, then we are going to find out different properties of Laplace transform, because for now it is good to go with inverse Laplace transform for a few minutes. Then there will be properties that we will be discussing in maybe the next class. So what Laplace transforms we have done so far? Laplace transform of t power n is n factorial divided by Laplace transform of e raised to at is 1 over s minus a. Laplace transform of sin at is, and that's going to be a over s square plus a square. Laplace transform, let's write sin hyperbolic at, I am not writing cos at, is what? And okay, this is what we call the Laplace transform, and this is what we call the inverse Laplace transform. Here your answer is always a function of s. And when I take this L here, it means you take the Laplace transform of a function f of t, you will always get a function f of s. And when you take L here, it means you take inverse Laplace transform of f of s, your answer is always going to be function of t. So what is inverse Laplace transform of n factorial divided by s power n plus 1? That is t power n. Because I take Laplace here, that becomes inverse Laplace, and my answer is t power n. But this is not the situation you will always get. This is not the situation. The situation will be take n factorial common out of it and then divide here. This becomes that. So you will get that, okay, what is the inverse Laplace transform of 1 over s cube? So you can apply this formula. This is s cube, so you have to write here 2. So t power 2 over 2 factorial, so 2 square over. This is the answer for the inverse Laplace transform of 1 over s cube. Because numerator will always be something like 1. And if you are exactly making numerator to be n factorial, then it would be very difficult. So this formula should be kept in mind. Similarly, inverse Laplace transform of 1 over s minus a is e raised to at, and inverse Laplace transform of a over s square plus a square is sin at. Even this is again problematic because this is constant. Take it out and divide it here. You will get functions of this form. Okay, when you get Laplace inverse of let's say 1 over s square plus 4. So you can write this Laplace inverse of 1 over s square plus 2 square. So your answer according to this formula would be sin 2t over, according to this formula. Similarly, inverse Laplace transform of 1 over s square minus a square would be sin hyperbolic at divided by a. But the question is that to find out inverse Laplace transform, we must know the Laplace transform of the functions. Is there any other way to find out the inverse Laplace transform? Because the problem is, when we integrate a function, we must know the derivatives, because we consider integration to be the antiderivative. Similarly, we consider inverse Laplace transform to be the inverse of Laplace transform. But this thing is not always good, because the problem is, to find out the inverse Laplace transform of this, you must know this formula first. But there is a formula in the case of complex variables that we can apply to find out the inverse Laplace transform. But that's simply very difficult. We must need some foundations of complex analysis. Then we have to evaluate that integral by using some advanced theorems in complex analysis like residue theorem and so on, because there is an integral. So it is very much difficult, but at least there is a direct formula to put the value and get the answer. But here there is no direct formula. Why this thing is equal to this? Because this, the Laplace transform of this thing is 1 over s minus a. Then you can readily consider, okay, Laplace inverse of this is going to be that. Otherwise, you must have a formula, like in this one you have a formula. You take this one, you put in the formula, you evaluate, you get this answer. But you don't have anything here. So this is the problem with these things. So you have one thing, one formula for this, but it's a complex version, it's very difficult. Like if I say you to integrate a function, if I ask you what is the integral of, let's say, sec square x dx, what's going to be the answer? It's going to be, I think, 10x. Why? Because the derivative of 10 is this. I don't have any direct formula, so I can do it, but I know just the formulas of derivation, then I can apply the formulas to invert the result. But I don't have any direct formula for this. If I am applying the direct formula, like you integrate this by definition, it's going to be very much difficult. Everyone knows integration by definition is very much difficult. You have to apply limits and so on and so forth. So it becomes very much difficult. Okay, any question from this?
So if we have a function of class function,
Yes.
then I need to
S.
divide s.
No, because it's a variable. You don't need to
I am
divide.
talking to reconvert it
No.
into inverse.
S remains same here. You cannot take S and divide it because S is a variable. I am doing it because A is a constant. Because when you get something like 1 over s square plus 1, you will consider this is a constant. The answer will be sin t. When you get s over s square plus 1, this is a variable, your answer would be cos t.
Right.
So you cannot take variable out and divide. It's not possible. Similarly, like if you have x, you cannot take x outside and you do the integrals. It's not possible because it's a variable. Okay, so let us keep the rest of the things for the next class, I think.